So the next topic that we want to go over according to the scheme of work is trigonometry. So that sounds really complicated, but you've actually done some of this already when we discussed Pythagoras' theorem. So it really isn't that complicated, and we're going to take it nice and slow over the next few lessons so that we all are really confident with this material. So our first lesson, you should have the sheet that I put in the Microsoft Teams chat as well, where you can follow along with the questions and everything. So the learning objectives are to remember how to find the hypotenuse, the longest side of a right-angled triangle using Pythagoras' theorem. Just one little note, when I say RAT, I am talking about a right-angled triangle. It's just a shorthand that I use, makes it a bit easier. Nice little acronym. We want to be able to label the opposite, adjacent, and hypotenuse of any right-angled triangle given an angle. Now that sounds really complicated because you may never have heard opposite and adjacent being applied to triangles, but we certainly know what the hypotenuse is. It's the longest side. So all of that will be made straightforward. So for the starter, what I'd like us to do is to label the hypotenuse of the right-angled triangle below. So if you want to give it a go yourself, you can pause the video, have a go, and then resume it anytime. So I'll give you a chance to do that now. Okay, so what we should remember is that the hypotenuse is the longest side. So I've indicated that earlier. Let me just get this one as well. So we can see here that should be this side here that I've just labeled there. Should be that side. But the trick is, because it might not always be that clear, is that the hypotenuse is always opposite the right angle. So we can see here, we've got this little triangle indicating 90 degrees. The right angle is there, and if I draw an arrow straight from it, opposite, the side that that arrow points to is the hypotenuse. So I can say hypotenuse. If you want to make a note on your sheet or in your book, you may. That's it, the right angle. There we go. So this, so I'm going to highlight it in blue, would be the hypotenuse. So what I've highlighted in blue is the hypotenuse. So what I always do, whenever you have a right angled triangle, if you draw an arrow from the right angle, the side that it points to will be the hypotenuse. So what I want to do is discuss the other sides of the triangle. So if I just draw myself an example, if I have a right angled triangle here. So we have our right angle in the triangle, and we know that opposite that is the hypotenuse, which I'm going to just label as hip. Then we also have these other two sides, the two smaller sides. Now, in a trigonometry problem, generally you will be given an angle. Well, you won't always be given it, you may have to calculate it, but to start with, we're going to be given an angle inside the triangle. So if I look at this angle here, I label it, say, theta. Theta is just a letter, it's a Greek letter that we use to represent angles. Then the opposite sides, well, what side do you think is opposite to theta? The hypotenuse was opposite the right angle. Well, if I draw an arrow similarly, so I'll do that here, do it in red. If I do an arrow from the angle, well, we call that side the opposite. So I'm just going to label as op. And then, well, we have the opposite, we have the hypotenuse, so the only one left to us is the adjacent. We can see that is right touching the bottom part of the angle. So we call that the adjacent. So our steps for labeling any right angle triangle are to label the hypotenuse by doing an arrow opposite the right angle. Then to do a similar arrow opposite the a similar arrow going from the angle that we're given, and that gives us the opposite. And then the one that we're left with, the side that we're left with, is the adjacent. So let me make another example, a slightly more difficult one. So see my exceptional artistic ability on display. So this time I'm going to draw it a little bit differently. So here we go. So I'm going to say that my angle is here. And this time I'm going to call the angle alpha. Don't be scared of these letters. They're just Greek letters that we use for angles. You may see regular letters being used as well, like X or Y. Just don't let it confuse you. So let's label a triangle. So first of all, we're going to look at the right angle and draw an arrow. Right, so we can see that the hypotenuse is this side here, and you can sort of see it. It looks like it in this case, but there are some triangles where it won't be very clear, but if you draw the arrow, you'll always be fine with it. So that is your hypotenuse. The opposite, well, to get the opposite, we look at the angle that we're given, and in this case, I've been given alpha. Now, normally you'll be given that as a number, but it doesn't matter if it's a symbol. So I'm going to go opposite there, and I can see that I hit this side. So that is the opposite. And then the side that we're left with is the adjacent, and we can see it is adjacent, as in it just touches the angle. And obviously it's not the hypotenuse, so it's this one here. So hopefully it should be quite clear how we label triangles, which is one of our main learning objectives today. So I'm going to give you an exercise to have a go at. I'd like us to label the opposite, adjacent, and hypotenuse of each of these right angle triangles. And if you remember, really, we should label the hypotenuse first, then the opposite, and then the adjacent. It's just the easiest way of doing it. So if you want to pause the video now, have a go at the exercise, and then when you resume the video, we'll go over the answers. Okay, let's go over the answers. So looking at my first question, A, right, I've got my right angle down here. If I do an arrow straight off that, I hit the side here. So that is the hypotenuse, the longest side. If I now look at the angle that I'm given, which is theta, if I go down and draw an arrow straight from it, I hit the side on the bottom, that is my opposite. And the adjacent is the side that we are left, which just touches the angle. Now, you may be wondering, what if I were given the angle down here? What if I were given an alpha or something down there? Well, that would be fine. You would have a different opposite and adjacent. In fact, they'd be the exact opposites. But I'm not worried about that because the angle I've been given is theta up here. So don't worry too much about that. For B, I'm just going to label them. Your hypotenuse should be here. Opposite should be there, according to where I've written it here. And the adjacent should be at the top. Similarly with C, your hypotenuse, your opposite, and your adjacent. There we go. And similarly with D, and you can see they're all different orientations, different, they don't all look the same. With D, if I didn't have that right angle, it wouldn't really look like a right angle triangle because usually we draw them like they're in A. So just get used to seeing them rotated differently. Worst case scenario, you can rotate your exam paper. So that is the hypotenuse, opposite, and adjacent. Hypotenuse, opposite, and adjacent. And here, hypotenuse, opposite and adjacent here. I mean, if you look at F, actually, it doesn't look anything like A. It doesn't even look like a right angled triangle. But if you draw the arrows, you can't go wrong. Okay, so hopefully you should have marked your answers by now. We can move on. So what I want to do here is just briefly revisit Pythagoras' theorem. Just because that will help us make this trigonometry a little bit more concrete. So if I go on here. So what I've got on here is some centimeter squared paper. So if you look at my ruler on the screen, so I've got my ruler in millimeter markings, but it doesn't matter. We can see 10 millimeters, that's a centimeter, and we can see that this is centimeter squared. It's all to scale. And what I've drawn is a right angle triangle with sides 3 centimeters, shorter sides 3 centimeters and 4 centimeters. You can just count them. And what I'm going to do is consider the areas of the squares that I could make by just drawing. So I'll just do it very crudely first, and then I'll do it accurately. By just drawing squares that come off the sides exactly. So if I have this bottom side is 3 centimeters, if I do a square, a 3 by 3 square coming off it like that, and then on the other side, I'm going to do a 4 by 4 square coming off it like that. And then obviously I'm going to do another one coming off the hypotenuse like that. So obviously that's quite crude. I'll do it accurately now. The reason for that is because I want to remember Pythagoras' theorem. I want to remember the relationship between the areas of these 3 squares. So if we just do that. So I'm just going to draw my squares a little bit more accurately than I just did. I'm going to put them in color as well. So if we look at drawing those squares accurately, if I do so, I will get something like this. So I've done the 3 centimeter square. I've done the 3 by 3 square. I've done in red, dotted lines in red, and the 4 by 4 I've done in blue. And then the square coming off the hypotenuse I have done in green. So let's have a look at the areas of these squares. So the area of the red square, well, area of the square, or the rectangle, is length times width. So the area of the red square is going to be 3 times 3, which is 9 centimeters squared. Or if you like, you can just count the squares. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I can see that the area of this square is 9 centimeters squared. Similarly, with the blue square, I'm going to get, well, I could count them, 4, 8, 12, 16, or I could just do 4 times 4 is 16. So the area of this square is 16 centimeters squared. Now, what I want to do is work out the area of the green square. Now, if you remember Pythagoras' theorem, you may well remember this. You can just skip ahead. If you've forgotten, that's fine. Let's see if we can work it out. So what I've got here is a duplicate of my blue square. And what I'm going to do is fit it at the corners into my green square, exactly like that. So there we go. So what I want to look at now is the area of the green square. So I can see that that blue square fits in it with some space left. Okay, so I can see that I have 16 centimeters squared here. And what I want to do is look at the space that is left. So I'm going to get, I'll use an orange. So let's look at the space that is left. Well, I can see that I have 4 centimeter squares. I have 4 centimeters here. So if I just extend these gray lines down a little bit, I can see that I have exactly 4 centimeter squares. Obviously, you've got to give a little bit of leeway because it's not 100% accurate, but it's as accurate as I can be. And then I can do the same sort of thing going vertically. there. And then what we could do to work out the area of the green square, well, it's going to be the area of this blue segment, this segment with the blue dotted lines, and it's going to be the segment that remains there, or the section that remains. So let's count the squares. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's go up in 5s, 5, 10, 15, 20, 25. So I can see that the area of the large square from coming off the hypotenuse is 25 centimeters squared. So if we look at the areas of the squares coming off the sides, for the red square we have 9 centimeters squared. For the blue square we have 16 centimeters squared. Like that should be 9, 16. And then for the green square, the large one off the hypotenuse, we have 25. Now, how are these three numbers related? If I ask you that question, well, hopefully you've noticed that if I do 9 plus 16, we actually get 25. So that means that if I take and honestly, if you look at the picture, that should make sense. You can see that if I have the blue square, and then I take the area, if I take the area of the red square, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. The bigger square is literally made up of the two smaller squares. So that means that I get the relationship that the sum of the squares of the smaller two sides of the right angle triangle is equal to the square of the hypotenuse. And that is Pythagoras' theorem. So I'll just go here. We see that the hypotenuse squared, or I'll say the square of the hypotenuse, equals the sum of the squares of the two smaller sides for any right angle triangle. So what I've done in the previous slide isn't really a proof, because it doesn't prove for any right angle triangle, but hopefully it just gives you a picture in your mind of why this theorem is true. Two smaller sides. So looking at the examples that I've drawn here, for my first one, I've got smaller sides A and B, and then I have hypotenuse C. I would have A squared plus B squared is equal to C squared. Similarly, with the one on the right, again, smaller sides A and B, larger side or hypotenuse C, larger side hypotenuse C, A squared plus B squared would be C squared. And for the bottom one, I probably have to label this just to identify the hypotenuse. I can see the hypotenuse is again C, smaller sides A and B, A squared plus B squared is equal to C squared. So this is all a bit abstract. So let's do a concrete example of finding the hypotenuse. So if we look at our first example, if I want to find the size of the hypotenuse, I could just again state Pythagoras. I could label my sides. I could label 12 as A, 13 as B, if I wanted to. The hypotenuse as C. Again, it doesn't matter if I swapped B and A around. So stating Pythagoras' theorem, the sum of the squares of the smaller two sides, so A squared plus B squared, literally just taking the smaller two sides, squaring them individually, then adding them up. That is going to be the hypotenuse, or the longest side squared. Then I can substitute my numbers in. 12 squared plus 13 squared is equal to C squared. Well, I can calculate this. 12 squared is 144. 13 squared is 169, so I can just say I've got 144 plus 169 is C squared. So calculating that, I get that 313 is C squared, and then I end up with C squared is equal to 313. And then, well, if I want to find C, I just need to essentially undo the square. So to do that, I can square root both sides, because square root is the inverse of squaring. So to do that, I'm just going to get c. If I square root c squared, essentially it will get rid of the square. There is obviously the issue of negative roots. I'm not worried about that here. So I get c is equal to the square root of 330, and I know c is positive. So doing that will give me, if I do that on my calculator, I will get my calculator now actually. Casio. Yep. Just so you guys can see, I would have the square root button is there on your Casio calculator of 313. Click equals SD, I get 17.691 and so on. So I'll say 17.69 centimeters to 2dp. There we go. So quite straightforward, hopefully, to find the hypotenuse. So we're going to do some further questions now. So this is on your sheet. If you want to work on your sheet, or if you just want to sketch the triangles, you can sketch them in your book if you want. There's no problem with doing that. So what I want you to do in this question is to work out the length of the hypotenuse. So you're given the two smaller sides in each case. I want you to find the hypotenuse. Then I want you to label the opposite and adjacent of the triangle. So really, label the hypotenuse first. So we can see here that will be the hypotenuse in the first one. Label the hypotenuse, calculate it with Pythagoras' theorem, then label the opposite and the adjacent. So if you want to pause the video now, have a go, and then resume when you want to go over the answers. So here are the answers. For the first one, well, we can label our hypotenuse just by looking opposite the right angle. So my hypotenuse is here. Then I can remember Pythagoras' theorem. If I were to draw squares coming off these sides, if I added up the areas of these squares, it would give me exactly the area of the square off the hypotenuse. So that means that I get that the sum of the squares of the smaller two sides is equal to the hypotenuse squared. So that's going to be 11 squared plus 5 squared is the hypotenuse squared. Or you could say this as the adjacent squared plus the opposite squared is the hypotenuse squared if you want to. So doing that, I get 11 squared, which is 121. 5 squared is 25. So let me just get my calculator on the screen for you. So we could do 11 squared plus 5 squared equals 146. So that means I get 146 is the hypotenuse squared. So just swapping the left-hand side and right-hand side around, I get hypotenuse squared is 146. And then I can do square root of ands, because the last thing I had on my calculator was 146, equals, I have 3.476. So I get hypotenuse equal to 3.48 centimeters, or meters, sorry, to 2dp. So for the other ones, I'm just going to do the answers. Well, first, of course, let's label it. So opposite the angle that we're given is 5, so that is my opposite. Adjacent to it is what I have left. That is the 11 meters. So for the second one, I'm just going to do this more quickly. For the second one, you should get the second one, you should have hypotenuse squared is equal to 17 squared plus 12 squared. And obviously, in an exam, you'd have to show all your work-ins. We would have 433, giving me the hypotenuse equal to the square root of 433, which is 20.81 meters to 2 decimal places. And then for question 3, we have similar sort of thing. Well, first, let me just label it actually, sorry. So if I look opposite the angle that we're given, we have 17, so that is the opposite. And then adjacent to the angle that we're given is 12 because it's the one left. I've got my hypotenuse, got my opposite, so 12 is the adjacent. Similarly, for the third one, opposite the right angle, we have the hypotenuse. So we can say hypotenuse squared is equal to 3 squared plus 4 squared, which is just going to be 9 plus 16, which is 25. So we've seen this example before. This is a Pythagorean triple. So the hypotenuse is the square root of 25, which is 5. And again, paying attention to the units, that's going to be centimeters. And then labeling the triangle, opposite the angle that we're given is 4 centimeters. So that is the opposite. And then the side that we have left is obviously the adjacent. Finally, opposite the right angle, we have the hypotenuse. Paying attention to the units now, it's all in kilometers. Hypotenuse squared is equal to 6 squared plus 8 squared, which is going to be 36 and 64, which is 100. So the hypotenuse is going to be the square root of 100, which is just going to be 10. Paying attention to the units, kilometers. And strictly, I should say 10.00 because I wanted a 2dp, but that's fine. Then looking at the angle I'm given, this time the angle I'm given is y, because you might have x or y, theta or alpha, you might have Greek or normal Latin letters, depends. It's not a problem. So if I look opposite the y, I hit the 8 kilometers, so that is the opposite. And then adjacent is the one that we have left after the opposite and hypotenuse, which is 6 kilometers. So that. So if you just mark your answers and see how you've done. If you're happy with everything done today, that is great. We've hit the learning objectives. You should be able to label any right angle triangle given an angle. So if I'm saying label the opposite adjacent hypotenuse when I'm given theta here, you could also be given an angle up here, say beta, and be asked to work out to label the opposite and adjacent there. And you can also use Pythagoras Theorem to find the longer side of a right angle triangle. So if you're happy with all that, you've hit the learning objectives for today, and I will see you in the next lesson of this series.